Thank you very much. Thank you very much. Good afternoon, everybody. I'm very happy to have you today. I want to thank you to be here today. Also, thank you very much, Georg, to give me the opportunity to talk in such a prestigious appointment. Today, I'm going to talk about a topic that stands at the intersection of traditional scientific computing and emerging machine learning methods. In particular, I'm going to talk about how to use machine learning, deep learning technology to solve a partial differential equation using this new technique called physics-informed neural networks, in short, PINN. The talk that I'm giving today is divided in 3 parts. I will first provide some detail about physics-informed neural network, PINN solvers. I also want to have a much broader background on using neural network for solving PDE. So we will spend a little bit of time understanding what are the basic technologies enabling the solution of partial differential equation using a neural network. In the second part, I will talk about a little bit optimization of the PINN solvers. So how can you improve the accuracy? How can you improve the computational performance of this neural network-based solver? And finally, I will spend a little bit time on describing how to integrate neural network technologies into technologies that are traditional, so linear, for instance, linear solver. So this is the more research part, the last part. So that will be more open-ended. Just a disclaimer on this particular talk. I want to say that these physics-informed neural networks have many applications, among which data assimilation task, uncertainty quantification task, and solving ill-defined problems. So problems for which a part of the problem is not defined. So for instance, we have a problem without the definition of boundary condition or without a closure in the system or without an equation of state. In this talk, I focus on PINN for solving partial differential equation, PD. So rather more focused approach, focusing on solving partial differential equation. So this task, they have a very similar formulation when using PINN, but they have additional pieces when it comes to the definition, for instance, of the loss function. As I told you, this talk is about how to use neural network for solving partial differential equation. Throughout this talk, I'm going to take the solution of a two-dimensional system solving the Poisson equation as a main example. Of course, these technologies can be applied to many different kinds of PDE, linear and nonlinear. But I will focus on an example that is very common, very famous. So we'll be able also to relate to other approaches that are used in traditional computing. So the formulation of this 2D Poisson equation is the Laplacian of u, where u is going to be our unknown function that is defined in a two-dimensional space. So we will have x direction and y direction, and then we will have a source term that we are going to call f. Then we will define the domain. So x and y are a point in a two-dimensional space where the length of the simulation box are 1. So we go from 0 to 1 in the x direction and from 0 to 1 in the y direction. So the question I have for you, I want to challenge you on this, is really giving you a generic architecture of a neural network, like the one we have here, fully connected. How you do it? So how you would, without knowing much, or if you know already about PINNs, forget about it. But how you think you will do it? Just to leave you a few seconds to think of how you would try to solve a neural network. Try to solve the 2D Poisson equation using this neural network. Well, to give you a little bit of help, let's assume that we have an analytical, for instance, this F is quite easy, so we can integrate analytically. That's a possibility, or we know that we can solve very easily this Poisson equation using linear solver. So we have the numerical solution. So the way I would do is the following. So I will have my domain here, the network that we're going to use, and then I will provide the x and y, these two variables, as the input of our neural network. Since we want to use this neural network as a solver, the output will be an approximation of our unknowns u, that we call the u tilde, at the position x and y. So that's the basic mechanism that we want to put in place. And this, we want to be an approximated solution of u at this point here that we give as an input. So now the major issue that we're going to have is really how we can define the error, right? How we can give find the error, or the so-called loss function in machine learning, that allow us to optimize the values for these grid points. So in the case we have an analytical solution, one thing we can do is to take one point here, give the x and y solution, have a forward pass. So we multiply by the existing values of on these nodes, and we calculate an approximation of u that will depend on the current values that we have on this node. Now, because we know the analytical solution in that particular point, because we integrated before, we can actually calculate the loss function. That is it's kind of average of the error. So we did this. If we take this point, we give x and y, we give a forward pass, and then we calculate what is this u tilde. Once we have this u tilde and we know the analytical solution, because it's given, we can go a back prop phase where we change the weights and the biases of these neural units. After we do one sample, we can take another one and repeat the same approach. Forward pass, we calculate the error when we take an average with the previous error, and then we keep in correcting. So we can sample this in taking a random number within this domain, and then take what is the approximated solution that we obtain by a forward pass of this neural network. We found that is this error, and then we calculate the loss function, and we make a break prop to change the weights and the biases of this neural network. If we have a numerical solution, we can proceed in a very similar way. The only difference will be that at this point, we will only know the solution of our solution at a certain point. So we discretize the space when we can use a linear solver to find the values of u only on this point, because we discretize. For instance, we can do a simple finite different scheme to calculate the values of here, and here. So we can take what are the x of x and y of these grid points, ingest into the network, and repeat the very same mechanism. Forward pass. The major difference here is that when we are going to calculate the solution, we will have another approximated solution here. So we can call u bar, because it's still approximated, because it's coming from numerical differentiation here. And these are defined only at the discrete points on the grid. As we done before, we can select randomly, or we can just go through all these sample points, and then we ingest into the network. We get what is the approximate solution. We calculate the error, knowing the numerical solution. calculate the loss function, and then use the values of left function to calculate the new weights and biases of the neural network using the backprop phase. So once we did this mechanism, that's at very least what would do, and that's what many people at the beginning of a neural network actually did. This is very, very simple scheme. And once we have our neural network, what we're going to have is we're going to have here, some weights and biases for each of these units on different layers that will allow us to grow just with one forward pass from some initial point. So we can just give, I want the solution in this point here. We give the X and Y coordinate of this point as input of our neural network. And then we use this already trained neural network, we trained it before, to get the approximate solution of U. Important point that I want to make is that PDE solver, so this is a supervised PDE solver because we use the analytical solution and we use the numerical solution, are griddless. So whenever we give actually an input here, we don't need a grid to be defined in our computational. So PDE solver using neural network technologies, you do not require a grid a priori. So let's talk now on the important topic of this talk, that is these physics-informed neural networks or PINNs. So PINNs are neural networks that encode a partial differential equation into a part of the neural network exclusively to calculate the loss function. So in the previous method, what I would call the naive approach, we actually use some data that we know before. That can be either the analytical solution or it can be the numerical solution if you use some linear solver to calculate the unknowns on the grid points. In this case, we introduce an additional piece to our neural network just to calculate the error that we are doing or calculate the loss function. We will still use all the machinery that we discussed in the previous slides, but we will add an additional part to the neural network just to calculate the error in the loss function. The PINNs have two major innovations when compared to the previous approach. The first one is that, as I said, we're going to add a part of the network or a graph to calculate the residual. So this is the residual that is often used in linear solvers. It basically gives us the element by element error. Right? So if we have a linear solver, A, where A is the matrix and X is our unknown, and equal to B, where B is the source term, B minus A multiplied by X will be a vector. But that is called residual. Basically, it's going to tell us how far we are from satisfying the solution element by element. So the PINN allows us to do a very similar operation to calculate the residual as we do in iterative solver. So the first part is to add this extra piece, additional network to calculate the residual function. And the second one is to leverage one important technology introduced by neural network, that is the automatic differentiation. And this we are going to use to calculate derivatives on the network. So this is nothing fancy, just the chain rule for differentiating on a graph. But it turns out that the backpropagation in machine learning
is based on this automatic differentiation. So we will be able to reuse these important technologies in PINN. Let's look at the first important innovation of PINN. As I told you, the innovation is that we are going to add an extra part to our neural network. So we have, as before, we have the so-called surrogate neural network that is exactly like the one that we saw in the previous slide. We're going to have here X and Y as input, and the surrogate neural network will give an approximated values of our solution. So this mechanism is the very same that we saw before. In addition to that, we're going to add a residual network that is going to encode our residual function. In this particular case, the residual function is just the Laplacian. We're going to take as the input the approximated values of this function minus the values of the source term, in this case, f. We're going to encode on a neural network this particular residual, including the boundary condition. Just for instance, in this case, we can take these values of u, take a first order derivative in the x direction, and then we take we sum it up we take then another derivative in the x direction, and then we sum it up to minus f, right? Because it's here, there is a minus. We can do the same thing here. So we take the first order derivative in y of this value. Then we take another first order derivative. So this is the second order derivative. We sum it up with the contribution coming from the upper part of the network, that is the second order derivative in x, and then we take minus f. So this will be at this point we are going to have what is the residual, right? And we can calculate what is the error using this residual here. So we can each point that we give as an input will provide one R that will allow us to calculate an error or a loss function, this mean square error, using the values of the residual. So we are not using anymore the solution of analytical solution or numerical solution to do the training, but we can let the residual to drive the optimization, the back prop, to update the values of the weights and the biases. Of course, together with these residuals and network, we can also put what is the residual on the boundary conditions. In this particular case, we want to have impose the boundary condition equal to 0. So we're going to have also an extra part for defining the residual on the boundary. So one important aspect and the reason why I call this is innovation is that the introduction of this second part on this neural network, the so-called residual network, allow us to avoid the usage of any knowledge about the solution of the problem, either analytical or either through simulation. So as we saw in the previous slides, this is way to do that will be, well, we know what is the solution from numerics or from analytical solution, and then we can create a surrogate model training by calculating the loss function using the data that we already know. When we add this residual network, the error will be given by our residual. So there is no need for a prior data. So we don't need to know the solution, the a priori solution of the
the network. So it can really work as a real solver, right? So we have a problem, we have a PDE, we encode it. There's going to be a residual function that is encoded in the second part of the network. And when we train, our iteration will basically forward pass to calculate approximated value. We get the loss function using the residual, and then we do a backprop to update the values of the weights and the biases. In some sense, this is much similar to unsupervised training techniques in machine learning, since we don't need any label or any knowledge about what is the solution to calculate the error weight. The second major innovation, so the first one is to add this residual network as a second part of the neural network. The second technology is really how we calculate this derivative on the graph. So we have here two derivative. So here we can actually leverage and exploit a technology that is widely used in machine learning that is called the automatic differentiation. It is it's basically applying chain rules on the network. So this is widely available in the TensorFlow and in the PyTorch. Just to give you just an idea how this is simple, I provide here an example from TensorFlow. So this is very nice, and it's very nice technology that we are getting basically for free from just using these deep learning frameworks. Already there, available, and of course, also automatic differentiation has a very nice numerical properties that I'm not going to describe here, but I would refer you to very nice either review or studies of automatic differentiation on graphs or networks. Just to summarize, how a PINN solver will actually work. So we do first the training iteration. We can choose a number of points. We can choose randomly or using certain sampling technique. There are different sampling techniques that are available, and then we repeat the following iteration. We provide as an input the x and the y coordinate. We make a forward pass. We calculate what is the approximated solution. We use the residual network. We calculate the error using the information that we got from the residual function. Once we obtain the information about the residual function, we use it to update the weights and the biases only of the surrogate methods. So this extra piece is really just to calculate the residual. Once we finish the training, we can just avoid this part here and then just put x and y on the point that we want to calculate our unknown function, and then calculate this approximate u. So this is a very emerging topic. So the first publication on this topic was basically 2018, 19. That's when this technology had been starting study. So convergence study, they started a little bit later on. So the effort in putting in more formal frameworks. It was only on later on in 2020 and very recently also 2022, 21. And so an interesting part is really that we can use pretty much all the machinery that we develop for classical numerical analysis for studying the convergence and stability of this method. In some sense, we can think the PINN as an iterative solver where each of the iteration is it gives us a better it give a new solution, a new approximate solution of the the problem, and increasing the training, the solution will change it, and the error will be, what is the difference in our particular case will be the residual, the norm of the residual. So the point I want to make is really that there is some machinery that we can reuse for understanding the stability first of these methods and also the convergence. In order to do that, we can use the same machinery and defining which kind of error are in the neural network, and when we study how they grow, or if they grow, the method is unstable, so it's not as good. But especially how fast the error decrease. It's possible to define a different kind of errors or generalization that is also typically called total error, training error, validation error, and do some analytical study. I would refer to this very nice important paper by Shane Dermon and George Karnadakis on making a first big effort in defining a formal framework for errors in machine learning, and treat the PINN as a linear as solvers. So that's the first step. So I'm not spending much time on this, but I will refer you to this important paper. So first, it's possible to do some classical numerical analysis studies of the PINNs, where we consider the PINNs as a solver, and also is possible to do some study on the convergence on the stability. One important results coming from Mishra and Molinaro is really that the PINNs require activation functions that are sufficiently smooth, right? So they don't need to have discontinuity in the derivatives. Otherwise, they won't be able to well approximate the solution of our problem. So what are these non-smooth activation functions? So probably the most famous is the rectified ReLU, Van-Dries exponential, and Cellus. So whenever we have something that is not smooth, so the first derivative is discontinuities, the PINN won't converge, right? So that means that increasing the data set, the number of the iteration, the error won't go down. So the activation functions are not expressed enough to represent the solution of our problem. So this can be shown theoretically and it's been shown by a series of papers by Mishra and Molinaro ATH. But also, the best way to convince yourself is actually run it. Right? So you can change your PINN and use one of these activation function, and you will see that the results are not very nice. You will be quite disappointed from one side, but also you will be very happy that the theory, is very strong, right? And it's always nice when theory and experiments they go together. So an important point is really be careful when you choose the activation function for the PINN. It turns out that most of the PINNs that you will find on the web, they do use TAN-H that is quite smooth, so that's not a problem. But if you are more adventurous and try different activation function, then you will need to be aware that there are theorems that tell you that if you are using non-smooth activation functions, you will have problems with the stability of the non-convergence of the problem. So at this point, the major question you might have is really what is the performance simple PINN and how it compares to traditional solver, just to get an idea. So for doing that, I'm just presenting a problem of solving the Poisson equation in 2D with this source term that combine different sinusoidal terms with different k, so with the different wave number. Right? So we go from small wave number from 1 to 4. So I want to have a source term, a driver that has a different wave number, or if it's with time, it will be different with different frequencies. I will explain why later on. I start from this particular example here. I'm using Python and DSL for a PINN called the Deep XDE, developed at Pacific Northwest Laboratory. Just for very simple neural network, I choose fully connecting network like the one that I showed before, 4 layers, 50 units per layer. The TAN-H activation function I choose as a sampling point, all the points that I choose randomly at the beginning, 10,000 collocation point. And then I will use a first part of up-down optimizer, and that is first order optimizer, and then a BVGS B optimizer. This is second order to speed it up a little bit. So here on the top panels, I have a contour plot of the solution. So we have the X and Y, and this is a different part of our training. On the bottom, we have on the X-axis we have the iteration point. I express in epochs. Epochs is the number of iteration that it takes to go through all the training set, where the training set is all the points in our domain. So you see that we go up to 10,000 epochs. So we basically go through this training set 10,000 times. And then here on the y-axis, I have the training error. Right? What is the MSE, that error that I defined before? And then I show the snapshot of our solution at different training sets. So one is basically here. That is around 500 epochs. One is here, that is 5,000, right? And this is this point here, and then we have this one that is basically 10,000, 30,000. So it's basically it's basically here at the end. So you see here, after we train for 500 epochs, this is the solution. We take for 5,000. This is the solution, and then this is at the very end of our training. This is a quite solution. At this point, also we can calculate what is the error. The reason why I choose this nice analytical solution is that I was able to calculate it's very easy to calculate the analytical solution by this, and we can calculate what is the error. So you see that the error is can reach 10 to the minus 3, and you see here when you have some the gradients part, when there is variation. Also here there is some quite big error on the boundary, right? Let's look at the part about how much does it take. Well, I did on my laptop. So this first part it took 46 minutes, and the second part took roughly 1 hour, right? So, and just to give you a comparison, if you use the PETSI, the CG solver, that is a classical way to solve this problem on the 100 and by 128, it takes 92 seconds, or 1 minute and a half for a fully convergence in double precision. So if I want to bring it to fully convergence to 10 to the minus 16, it will take minutes. So the traditional approach is much superior to this direct PINN usage. So I was a little bit disappointed when it was quite disappointed when I did this. I was expecting something better. So then, I tend to live, with passion the research part. So I try to understand how this can be possibly true. Of course, I was doing many optimization were not possible, and how to improve it. And this corresponded to the second part of my presentation. That is, can we actually improve the PINN solver, the basic technique that I showed you before? And it turns out, yes, so there are some basic things that we can do right away to optimize the performance of the PINN. The very first one is really the activation function. Activation, so choose an activation function. And one experiment that I did is to use different source terms. So they give a different solution, also a different nature for the source terms. One that is very smooth, that is the one that I used before, smooth, and then one that is basically discontinuous, so it's not smooth. So this basically is just taking our box and then put 2, 1 in the circle here in the middle, and the rest is 0. So 0 here, and then we go pop, here in the middle, 1 is like a mesa, and then is 1. So this continue. So the first point I want to make is really depending on the problem that we're going to solve. In this particular case, on the source term, we want to use a different activation function. So in this case, we saw that this part, so the red one, so this swish function is quite good, and then also the tan h is quite good. So the problem here is quite smooth, right? So we saw that quite this smooth interpolation function or activation function are quite good. In the case of this non-smooth source term, we saw that the sigmoid that has much more steep behavior is much better, give us much better performance. Well, I talk about performance here in terms of accuracy. On the y-axis, we have the error. So these are comparison of different activation function. We want to use the one with less error. So that's the first results. And so the activation function impact the error, and that is, if you think about it, you can think as activation function in neural network as nonlinear interpolation function. For instance, if you think on finite element methods, there are some similarities. It's not one-to-one matching, but the way that may think as some nonlinear function. Of course, the better and most suited interpolation function you have for your problem, the faster you will get. So we're expecting that. We also expect that it depends on the problem, because you might have different interpolation function that match to different problems. Another important point is that the so-called local adaptive activation function that introduce an adaptive local scaling local to the layer. So there is some adaptivity in the function. They provided the best performance in terms of residual error. So in this case, for instance, you see that these local adaptive activation function 5 and 10 are basically two scaling factors that we introduced. And also here we have the lab that perform quite well. So optimization, if you want to do some optimization, we should start from an activation function. The second part is really about the optimizer part, that is the FGS. It turns out that we want to use a second order optimizer that provide the fastest convergence. However, we need always to give a few iterations using the low order optimizer like Adam, just to avoid it to get stuck in local minima. A major issue here is that these technologies, some are not ported to GPUs, but now are basically becoming available today on GPU. The last optimization we can do is actually to use a technique from machine learning that is called transfer learning. That is basically about how we initialize the weights and the biases of our PINN. So we can use some traditional initialization of the weights, but that's still random. But what we can do is to solve a problem that is similar, and then train it and use that as to initialize the weights of the problem that we want to solve. So it's kind of pre-processing technique. We solve a different problem, all right? Still similar in some sense, since it might be the same equation but with different source term. We train it as much as possible, and then when we solve the real problem that we want to solve, we initialize the weights and the biases using the results of this problem. In some sense, we say that the first PINN, the one that we train solving equivalent or similar problem, is transferring all the knowledge to the second PINN. So it turns out that even after all this optimization, the PINN is not as good as a traditional iterative solver. And I move now to the third and last part of my talks, that is really, can we combine the two different approaches? So we know that machine learning might be a good approach, but traditional solvers are actually very, very good, and it turns out also, even after this optimization, are faster than a PINN. So the idea I want to have in this last part of my talk is really, can we combine two approaches to get the best from the two worlds? And the question that we need to ask ourselves is really, what PINNs are good at? It turns out that neural network, deep learning in general, are characterized by the so-called F principle, the frequency principle. So this is a principle that applies to all the neural network. And this is a principle, so there is no proof, but there is experimental evidence. So this principle states that deep neural network often target function from low to high frequency during the training process. What does it mean? Well, this means that the neural network, in this particular case, the PINN, they solve first the low frequency components of our problem. So, for instance, if we have a solution that includes many different components, it will first solve quite well the larger scale features, and then going and fixing the small scale features that are corresponding to the high frequency part of the solution. Let's tell you why I choose this part here. So you can see here on this plot here, we have a different iteration. You see the first feature start emerging first here, and when we advance, we start solving smaller feature here that were not so accurate at the beginning, and then we finish up with all these smaller feature. So the part here is really that we can use this one to use PINNs to solve the big, larger scale feature in our solution. It turns out that if you're looking at traditional basic techniques like traditional Jacobi or Gauss-Seidel solvers, these are iterative solver, the convergence is actually works in the other way around than neural networks. So they actually converge on the smaller scale first, and that's so you see here. For instance, we have a random solution at the beginning, and then we saw the Poisson with some boundary condition here. And we see that the Jacobi iteration is fixing first at the small scale and then it propagates. This is, of course, a consequence of how the method is actually working. This traditional method is that requires that the information from one point to the other one just propagate on the neighbor cells. Right? So we have a cells ij, and then this use only the information from the neighbor cells. It doesn't use the full things. So this basically intuition led me to try to combine deep learning solvers with the traditional classical iteration using this strong the fact that deep learning networks converge on large-scale structures, and then Jacobi is the opposite. So the basic idea here is that we can use and train a deep linear solver on a coarse grid, so we can capture all the larger scale structure at the beginning, right? And then we let the Gauss-Seidel iteration to refine and improve locally the solution. So we use the deep learning framework. We solve the big structure that will take a lot of time for the Jacobi or the Gauss-Seidel information, since the information propagate first. So we jump up, we solve first the low course, and then we refine the solution. Of course, we can refine with the Jacobi, but also we can use some multi-grid technique, very basic one, using different grids after we use the initial Gauss-Seidel iteration. I don't have time to go into detail to this, but I can provide the reference to the paper I describe this. And here I show some performance of this hybrid technique. You see that this case we need to introduce a grid because the method is hybrid. And you see that the error now is going way lower at the fraction of the computational cost. And also you see that this hybrid method is much better to deal with the boundary condition. So this is reasonable. There is no big problem. When it comes to the computational performance, I tried different resolution tolerance for hybrid methods. So this is just an example for a small grid using first the deep learning and then the multi-grid, Gauss-Seidel plus multi-grid. And this is just a normal Gauss-Seidel, and this is just normal PETSI SG. However, this is quite a small problem. When we go up on the grid point, you see that the execution time for the hybrid methods is similar to the execution time that we have using some traditional approach like SCG. I want to just wrap it up. I'm running a little bit late. So I talk about basically three topics today in this talk. First, PINNs are neural networks that encode a partial differential equation in the network, and they can be used for solving PDEs in a supervised fashion. So we don't need to know the solution. So they can act as a normal solver. Second point is the PINN performance. Both the computational performance and the accuracy is still far from performance of traditional approaches, especially the direct approaches. But optimization are possible. So we need to choose convenient activation function for the problem, high order optimizer, and any advance on the high order optimizer will lead to improvement here, and rely on transfer learning for avoiding some cold start of the neural network. And finally, I spend a little bit time on combining, on discussing the combination of traditional and PINN solver technologies. And this is a realistic approach for developing next generation solver. However, I just want to emphasize this is just the infancy of this development of these methods. So there is still a lot of work to do and to improve this method, but the path is very promising how to combine and how to get the best of the different approaches. And with this, I'm done, and I'm happy to take any question.
Thank you for your presentation. I have one question. If I normally train a neural network, I do this on some kind of training set, and afterwards I want my network to generalize to other problems. How would this be in this case? If I have trained my network for a very special situation, would it generalize to different, say, boundary conditions of the differential equation? Or is it just a solver for one specific problem in the end?
Yeah, so the training set is just the collocation points, right? But if you change the problem, so for instance, you change the boundary condition, you keep the same equation, but you have different boundary condition, or you change the source term, right? So then you need to retrain the network, right? So you need to retrain. So one feasible approach to avoid this, to overcome this big issue that you change the problem even slightly, you need to retrain. Then you need to use this transfer learning, right? It turns out that transfer learning works quite well. So if you are solving a problem that is somehow similar, right? So as a similar boundary condition or similar source term, or there are different techniques also to how to devise transfer learning, but you can have achieved non-linear sort of exponential convergence at the very first in the first phase. So to answer your question, you need to retrain all the time, and that's a big bummer, right? And but you need to rely on transfer learning. So, for instance, if you have an application that at any iteration is basically solving the same problem, but with different source term, so it might be just electrostatic potential, and when you have different charge density, the charge density will be different each iteration. So you can do a very good training the first time, right? And then at each iteration, the source term will be very similar, right? So we'll have a quick convergence to the problem. But to answer your question, you need to retrain. Hopefully, you have a fewer iteration in your training. Also, another issue might be that as I showed, is quite bad for the small scale structure, right? So then, depending also on your problem, the frequency that are in your problems, or how smooth are your source terms, you might less or more effective the deep learning. But just to summarize, yes, you need to retrain, but there are some techniques that will heavily reduce the number of iteration.
Okay, I see. Thank you. So one question related to that. You said if in your whole system you don't need to solve the underlying differential equation. I think it is more meant in a way. I mean, you need the solution to train all the network and this stuff, but this solution is produced automatically. Is that what you mean?
Yeah, exactly.
Okay, so the the second network, this residual network, basically solves in an automized way the differential equation.
Exactly like you do in iterative solver, where, or like a Krylov solver, where you have a residual, and then you're going to minimize in the Krylov space. You choose the way.
Okay.
So it turns out that so you can actually formalize, this method as real solver is quite complicated. The technique to solve this quite they have low accuracy, right? So that's why also it's important to use a higher order optimizer, because compared to a CG or a GMRS, they have way less information on where to find the minimum. Right? So definitely will be very interesting to understand if it can be embedded some of this technology coming from Krylov solver in this.
Okay, but then coming back to my first question, what do I win in the end? Because to solve a problem, I have to solve the differential equation to train the network, and then my network gives me back the solution. So what do I win?
No, so
it does not generalize, I mean.
So you're not really solving. So probably it was not clear in the previous question. So the extra network just give you a mean to calculate the residual, right? It's not really solving, right? So it gives a point, and then it calculates what is the error. So in that sense, it's not really solving the numerically the like you would do in numerical solution. So,
okay, but what is then this magic? Because if I can tell you the error, I need to tell you the error, I need the solution. Otherwise, I can't tell how far I am away from the solution.
Yeah, but so at the very first part, I showed the neural network where we know the solution, right? Numerical solution, and we calculate the error using the numerical solution. And that has no advantage. There is no point, right? It just pedagogically to introduce the topic. That doesn't make sense. So the PINN doesn't need that part at all. It just introduce an extra part that is encoding the equation in the graph, and use the graph to calculate what is the residual for a certain point, and then use that information to basically optimize the other part. So the major difference is really how you calculate the loss function, right? In the first case, naive, useless way. You use a kind of supervised. Either you have the analytical solution, the numerical solution, you calculate the error, you propagate. In the second, that is the PINN way, you calculate the n that is coming directly from the graph, right? So it's not you have some labels or some solution that you feed in. So it's coming within the graph, and that drives the optimization, and that is the PINN.
Okay. But
the first approach is, as you mentioned, is useless. It's not useless. He has some. People do. At the beginning, they start doing that. When I think myself, I would do right away. It's like this, and many methods actually are doing like that, but it's not much. There might be some advantage of having using this method just as surrogate. So if you have a less calculation, so if you have a nonlinear problem and you have very difficult problem to solve, might be require less calculation to have this surrogate method. But still, you will need to train in a certain way. So it's good. But the PINN doesn't allow to know. You don't need the solution to know the solution of the problem. You do need to know the structure. Right, which PDE you want to solve, and you encode that in the graph that will give the residual in one point that will allow the optimization. Is it clear?
Okay, I think the next hand was Aditya Kashi. Hey, yeah, thank you very much for the nice talk. My question is related to your statement about the frequency properties of deep neural networks. So is it really that general, or does it depend on the architecture of the network, whether it tackles the low frequencies first and then moves on to the high frequencies?
Yeah, that's a very interesting question. Yeah. So is if low and high frequencies is really relative terms, right? What is low and a high frequency, right? So first you need to have a system that comprises a number of different frequencies, right? And so it's relative to that particular problem. Having said that, I think the paper that I mentioned in your paper refers to convolutional networks, right? There's a similar study or a similar presentation by George Kaliakis where he shows also, because you can do the spectral analysis, that's super cool, of these things. It does with the fully connected. So when it comes to architecture, these PINN are still in the infancy. So for instance, recurrent neural network or some idea of the time within the architecture of memory are not there yet. You can see now first PINN using a group, but it's highly dominated by fully connected and convolutional network. Then the convolutional network will also depend how big you're taking, and the F principle definitely holds there. Right?
Okay, so perhaps it's related to the globally connected nature that gives this global coupling of all the degrees of freedom of all the weights and biases, and that's what leads to a more low frequency friendly system. If I had sparse neural networks, then in theory I could design a neural network that exactly mimics a Jacobi kind of nature, maybe. But yes, thanks.
Yeah. I think you pointed out I think you made a very important point, right? You can actually express traditional methods, making like more sparse, and using PINN, right? You can do the same thing, and these are called. That's one of the most interesting aspects of the PINN works. It's called discrete PINN. And you can, when it comes to the residual function, you can actually take only a discrete times or points, right? So you define the residual only on the discretization points that you will use. For instance, if you want to do Jacobi, and then you can calculate. The some weights to have new numerical methods. But at that point, then you will need to have it's not supervised anymore, but you will need the help of some high definition, high resolution simulation. So you made two important comments. So the large scale instruction might come from the fully connected part. I think that's very, very plausible and very good point. It might also come from, if you have a convolutional network, from how many points you have when you calculate the convolution, right? So there are some convolution networks here that take the old domain. And the other important point, I'm very happy that you made, is that you can actually express Jacobi or Gauss-Seidel as a graph, right? And this will give a sparse, and that probably also is the locality. So you made a very, very, very exciting point. And so you make me happy to be here today, because you make a step forward. Very, very interesting point is a fundamental things. I
I like this fundamental work. Just trying to have a better understanding. So I'm very glad you made these 2 points.
Yeah, thank you.
Okay, next was Jonas Schmidt, I think.
Yes, so thanks from my side for the very interesting and insightful talk. So I have a question about the optimization part. So there you mainly highlighted the importance of the activation functions, but I think so this something that also came up with the last question. So how important is the architecture of the network? So I've seen that, for instance, other architectures besides these fully connected architectures have been proposed, like these Fourier networks. Also, you mentioned convolutional networks. So is there perhaps also some work about neural architecture search for these PINNs, or is this a completely new area?
I think yeah, that's a very, very interesting point. As mentioned before, is the very exciting part to understand how to map either the structure of the PDE into a neural network on the graph, right? So how these two abstractions can go together. I do believe that it is an important and needed step towards integration of these new methods with the traditional ones, and I do believe that each architecture will best fit to a particular PDE. Now, having said that, so this is just the infancy. Like 90% of the PINN works is on fully connected networks. There are more results on convolutional networks, right? And it's very likely that, for instance, convolutional networks on a problem like the one that I show, a Poisson equation, if you take like a big stencil, those will be the most performant one, because they're basically what you need to solve a Poisson equation. It's basically convolution in the most elegant way. So I strongly believe, that each problem matches to a particular architecture, but this is, I don't have any experimental data, any results on that. So I have to say that my feeling, my intuition is that some architecture are best fitted to certain problem, and so not only activation function, as you mentioned, but also architecture should be an additional tuning parameter. This is very, very interesting and exciting, because it's really understanding the natures of PDE and how to realize this on formulating on the network, and which degree of freedom to choose a certain architecture give you, right? So if you're solving like a hyperbolic problem, right, or you do need some kind of a memory in the system, right? So I will feel uncomfortable to go for a hyperbolic problem without having some idea of the past. Now, just give me something instantaneous like Poisson equation. Poisson equation then is information is propagating instantaneously. Velocity propagation is. So to answer your question, yes, I believe that architecture are an important part of this tuning effort, not only activation. I focus on activation because I don't have any results on different architecture. I have results on different capacity, so increasing the number of units that allows to basically provide more expressive power to your solution. When you want to describe more complex, you will need more units and more depth. So that's why, but also the convergence will be slower, right?
So yes, if you do the full thing, you would get better performance, more expressive. But to go to good solution will take you some time.
Yeah, so totally makes sense. And what would be interesting also, so since you integrated your network into a multigrid like solver, so one other option would be, since you also mentioned that it would be possible to directly model numerical solvers within the network somehow, to have like a multigrid-like architecture within the network itself, right? Like these unit architectures that are popular for convolutional nets. So has this been tried out, or do you know something about research in this area, or yeah?
Yeah. So especially the group by Karniadakis at Pacific Northwest, they are working on. So there are so many different approaches. So I saw a recent journal of computational physics that was dealing like with the multigrid, but I didn't read it. It's very, very, very recent. I don't know which technology it is. So it's very new topic, right? Pretty much all the people is working on this now, right? So what you're saying, what we discussed today, is really pure research at this point, right? So I heard, very, very exciting, topic that you mentioned today. There is a growing number of papers, but it's really. So, for instance, they sent me this multigrid paper a month ago, basically to tell me that I need to hurry up with my research. So I feel a little bit panicking sometimes when I look at this work. So, just to summarize, there are many things that have been trying. I didn't see major work on integration of classical and machine learning, but there is an example from JCP from last month on the multigrid solver. The possibility of developing such a technique are very, very big, right? So I mentioned multigrid. Another things that I would like you to invite you to think about is about preconditioner. That's something that I didn't talk about on this, but clearly this PINN can play a role also in designing new preconditioner. Because they can give you a good solution, okay solution very quickly, right? But to go to the accuracy that scientific application needs, you will always need some traditional expert. So multigrid is something that research is needed. There are some very initial work, basically now, on this. So if you're interested in this and exploring this, I highly encourage you to do that. The other part I think is very promising is really to employ these PINNs in preconditioner. That's a clear space, and that's something that can be done on using green function. There's a paper, it was very, very nice on green function based preconditioner. So that's an area where I see where this can be combined.
Okay, thank you very much for the detailed answers.
Sure.
Okay, I think Christy was next.
Yeah, thanks a lot for the talk.
Yeah, sure.
So I was just wondering, like, when you basically use in the course grade the PINN, right?
Yep.
So and in the last comparison, you had comparison with Gauss-Seidel, for example, and the one with PINN, for example. So I didn't understand that one. So did you use Gauss-Seidel with multigrid, or was it just a plain Gauss-Seidel iteration?
So I did the hybrid that has the deep learning and then the Gauss-Seidel multigrid. So I just do one iteration of a Gauss-Seidel, and then I use a finer grade, do this multigrid steps. Then I compare the performance to just a Gauss-Seidel, right? Just Gauss-Seidel, and that's one of the plot. And then, and then there is the CG, that is the PETSI CG. So that would be a production grade linear solver, what an application today would use. An application doesn't use Gauss-Seidel.
Yeah, that's what I was thinking, that it was also a comparison with a multigrid, just plain multigrid without the spin, for example.
Oh, yeah, that's no, that's yeah, that's a good suggestion.
I think that would make much more sense, right? Because it would also, for at the coarse grade, also maybe Gauss-Seidel can probably.
I completely agree with you. I also understand how to combine these coarse grade solution on that are deep learning based, different coarse grade, and how to find different scheme to do interpolation.
Yeah, I was just wondering what it was.
Yeah, because one of the points that that now you're reminding is because one of the most powerful things about this spin is that they don't require a grade.
Yeah.
So it's true that I'm using it on a coarse grid because we know that they are good on large scale structure, right? So we just got it without solving the low level structure. So is but to have on small number, we can basically get the values on approximated values from at any point, because there's a continuous solution, and that's open up, to different schemes when you actually combine different grids. Now, I did a solution because it was the simplest, and that came to my mind. Some for the study would be, how you can combine on different grids, because you can have the solution using deep learning grids, but that requires some math, some math how to design. But so you're right. So for comparison, there should be also just normal multigrid, and then I think the most important point coming from my discussion with you would be to use this spin a different grid, and then because since it's gridless, you can get quite okay solution, right? So you can use this.
And also,
a very, very good point. Yeah.
And also, of course, for large grid, it doesn't matter when it's gridless, for example.
Yeah. So I completely agree with you. It's just an example. So it's very difficult to do a very meaningful comparison, right? Because you have different tolerances.
Yeah.
So there's a sweet spot, right, on the tolerances, how much you want to do to the deep learning training part and how much you want to do to Gauss-Seidel iteration. And so also the errors, it's difficult to compare to the same error level, the record. So it's just the plots that I presented you is more to give you, just to give you an idea how much we can do, right? So we start with the first direct PINN that anybody in the world just taking the PINN would do it, right? You download the PINN from GitHub, and then you say, oh, I want to understand how good it is, right? And then you see to get an okay solution will take 1 hour or 2 hours, right? And when you say, well, then you do some optimization, and to get okay solution will get you, 5 minutes, right? But then using this intermediate step, and combining different approach, then we'll combine the ballpark or traditional state-of-the-art solver. So now, how correct is this comparison? And the correctness part is really just the message that we are basically there, right? But only if you combine the methods, right? Or if you integrate, or if you integrate these methods. Now, the integration that I did in this multi-grid is very ugly. It's not elegant at all. So some of the suggestions I heard today, you can actually embed the Jacobi or Gauss-Seidel. If, for instance, Jacobi, you can just encode it in your graph and use sparse connection instead of a full connection.
Yeah.
And you can train those. Those are much more elegant approach to do this job. So to summarize, the comparison I have there, they give you qualitative aspects about where technologically we are. It's clear that a deep learning based solver need to have also the classical part or some knowledge of numerical analysis, right? So you need to embed not only the PDE, this continuous PDE, where you keep the continuity from this automatic differentiation, but you also need to inject some knowledge of the numerics, right? And to go to the next level. The way that I did it, I injected in an ugly way, right? Not embedding in the graph, but basically stepping between different methods. That's a possibility. More elegant approach is the one that I heard today. But also I suggest in the paper that I published on this topic, because I thought that was the most beautiful approach, but that requires somebody with a little bit more math inclined than me, or it will carry me some time. I'm sure maybe I can do it, but I would strongly recommend you to look at this, because it's an interesting topic. Many of the works that I'm doing are not very useful, so I always don't give suggestions on research direction other than some stuff that is applied. But if I had time, I would work on this, because I feel.
Also, one thought I had is, would it also make sense? Like, I have seen some work with PINNs where instead of this BFGS, for example, or this optimizations, they use a spectral or eigenvalues of the NTK matrix, neural tangent kernels. And then they adapt the weights of this, for example, when doing this optimization. Does it make sense to do that, or is it too costly to do that?
No, it makes sense. It makes sense because the PINNs also inherits all the problem of neural networks, in particular of this vanishing gradient problem.
Yeah.
And that's very, very visible when you deal with the boundaries.
Yeah.
So any optimization, especially if you have any adaptivity or any insight from the problem itself, has a lot of value, right? Because no matter how expensive it is, because it's basically injecting some knowledge of the problem into the graph, and also fix some of the problems of neural network in general, like this vanishing gradient problem, becoming very, very serious on PINN. You see in the boundary. So if you remember, the first graph, there's some issue on the boundary, that's very difficult. It turns out that Jacobi or Geissadler are actually a poor man way to fix also the boundary condition, right? Because you give a couple of iterations there and you fix perfectly the Geissadler. So I think, in my opinion, different people might have a different opinion on this. In my opinion, from my experiments, I would say that there is values on these more advanced methods.
Thanks a lot.
Okay, last question by Sirivas.
Yes, regarding the PINNs, physics from neural networks. So you said that we need a certain amount of training data for. Am I audible?
Yes.
Yes. So we require certain amount of training data for mapping the entire differential equation onto. Into the neurons. So in neural network, it's just generally weights, activation functions, and then we get output. So regarding this mapping, so how close is this to the analytical mapping? Let's say I take a very simple case of a heat equation in one dimension with constant diffusion coefficient. Let's say it will just be a second order differential in one independent variable. Let's say d squared t by dx squared equal to some constant. So so for such differential equation, there is analytical solution already. So in the analytical solution, there is a mapping of variables, let's say temperature, and I get the final answer. So how close is this mapping to the mapping of a neural network?
Not sure I understood your question. So you're talking about the training data, right?
Yes, no. After training data, when the weights of the neurons are formed, weights and everything. So this neural network will map the initial data by solving this differential equation. So how close are for simple equations like these, we can get analytical solutions. We have an analytical solution, yeah. So how close is this, analytical solution, the mapping of analytical solution to the neural network? So if we could find a link between these two things, I think we can extend this to further dimensions and further harder questions which can't be solved analytically.
Yeah. So first of all, you can solve any equation, especially non-linear.
Okay.
Right. So you can encode in this residual function, right? So you just encode it. You don't really need, what we call typically training data, where we have, the input and we know the output and we do that, right? So it just we know the input. So we just give you input. We sample on this grid.
Okay.
We take it. And then we just make a pass.
Okay.
And then one pass of the neural network will give already the error, the so-called residual, without actually knowing what is the solution, right? So that's why I call it unsupervised, because you don't really need to know what is the solution there. It's just an output of the second part of the neural network, what we call the residual neural network. And then it will give you the error, right? Without using any solution, a priori solution. And then you use that to calculate the weights. After you get, you can choose the grid, the input, right? In your domain, you can choose randomly. Or there are some technique. I didn't discuss those, how to choose the initial points, right? So you choose the initial points when you just choose the initial points and when you do this training. After you train, after a certain number of epochs, at that point you have all the weights on your neural network, right, and the biases. And then you can use it as your solver, right? So you take your network, you give different points where you want to know the solution. It might be on a grid, right? But also it can be any point within the domain. That's a quite powerful feature of the PINN, that doesn't really require a grid, right? You can take any point and then feed into neural network, and you will get what is the proximate solution there. Now, once you have this, of course, you can estimate what is the error, right? Because you want to compare to other solvers, right? So you know what is the analytical solution, and then you can understand what is the error of the PINN. So that's the thing. So now, so the interesting aspects also on this, right? So because so the one thing that you can also do, you can do. Let's say that you train, and then you can and you get as output the residual, right? From the residual graph. But also since you know the output that is this residual, you also know what is the error on particular point. So one technique you can actually do is to focus your sampling. So you do the training using input points where the error is maximum. So one thing you can do is to start with your collocation point and randomly, and then you can see where the residual is higher, and then choose most of the input points in that area, right? So you're giving as a training more points on the area with the more error, so the higher is the residual. So one possible technique is also to adapt the sampling to the residual, but this is more like advanced technique. Now, Servinas, I'm not sure I completely answer your question, but please.
Yes, I think I got my answer.
Yeah. Okay, thank you.